Hey, welcome to part 5, continuing the quadratic function journey. Hey, I've got some good news and some bad news. Uh-oh, here's the bad news. The batteries are still flat. So what are we going to do about this form here? We've just been doing some stuff with it, like finding where the graph cuts the x-axis. But what could we do in terms of finding that turning point when it's in this form? Okay, let's just look around the screen again. Here's y equals x squared. Here's x squared plus a, x squared plus 2, x squared take 4. Remember that one. Here's neg x squared, and x plus 2 squared, or x take 1 squared, x translations. And what about dilations or stretches? All of those are great when it's in that completed square form. Okay, the y equals x take h all squared plus k form. That has heaps to offer, particularly when your batteries are flat. So let's have a look at handling this expanded form here and see if we can get it back in that easy vertex form to find the vertex. Come on down and let's have a look at what we know. Okay, we know some good stuff, like how to find where the graph cuts the x-axis when it's in this expanded form. What do? We reverse FOIL, we factorise it, and it cuts the x-axis when y is 0, when the function is 0. So by the null factor law, either the first factor is 0 or the second factor is 0. It's going to cut at neg 3 or 1. Okay, so that's what we've been doing. Let's just graph that one there, neg 3 or 1. So here it cuts at neg 3 or at 1. We've got a good idea of what's happening here, something like that. But really would be nice to go back to where we started and look at this vertex as a translation of the vertex of x squared. If only we could get it in that form where that's easy to tell, x take h squared plus k. Alright, well that's the journey, and it's going to be called completing the square, making up this perfect square or vertex form. Just before we do that, do you notice anything about these numbers down here? X is neg 3 or x is 1. I think you see something straight away. When you multiply them together, you get the product of them here. We call this the product of the roots of the equation, or the x-intercepts. What about this number here? They're closely associated by FOIL, aren't they, to this number, because this is minus the sum of the roots, and that's always got to be true due to the FOIL process which we use to produce this function. So if you add these two up, neg 3 plus 1 is neg 2, and put a negative in front, you get plus 2. That number in front of x is minus the sum of the roots. Interesting little result there. That's going to be important later on, not so much in this course, but in later courses. Let's go down and focus on seeing if when we've got a form like this, we can package it back up to find the vertex. Now come down with me now and let's have a look. That's what we want to do. Isn't that true? We want to do that because then the h and the k, the vertex or the turning point, is hk. Can we do this? Big if here. Just change that function into a perfect square form. Come on down and let's have a look at the perfect square form and see if that might help us. Here's a perfect square. When you have a plus b and you square it, it's a first term squared plus twice the product plus a second term squared by FOIL, if you like. FOIL can be used to show that. So spreading it out, it's the square of the first term, twice the product, and the square of the last term. Let's take these first two terms here and see if we can see a pattern. So it's always going to be square of x, yeah? What do we put in here? Or it could be a minus, couldn't it, in here? We don't know. Let's just rub that out for the minute. What goes in there to give twice the product? Well, there's a 2. And there's x. Now x is that term, so the 2 must be twice the product of the other term. Okay, twice the product here, because we know one of the terms is x 2b must be that too. So b must be half of that, or 1. So it would be x plus 1 all squared would give us x squared and 2x. And so what have we actually added on there? 1 squared, which is 1. So let's take it off so that the balance of the equation remains the same, and then bring down -3. So what do we got? X plus 1 squared, take 4. If you expanded that, it'd go back to that form there. Okay, what did I just do? Pretty complicated. Let's go down and actually summarise it with this statement here, completing the square. What did we do? First of all, repeat the line, so it's x squared plus 2x. Then we halve this, because that twice the product term, so halve that, and that was equal to 1, halving it, and then squaring it was 1 squared, and we're going to add that on. Now that process of halving the coefficient of x, or number in front of x, squaring it add on, always will produce that perfect square pattern. Okay, we've added 1 on. Okay, we've got to subtract that value. So we've got the 1 added. Let's subtract that value and bring the other 3 down. We'll still have that. Well, this is the little tricky doing here. We need that 1 to make this square. But we can't just add 1s to an expression. Won't keep the y equal to that. Won't keep the balance. So we take it away. And what's the final constant here? -1 take 3 is -4. So we can then, we've restated the expression in squared form. Now we've made up this square, but we've got to do all this adjustment so that when you expand it, we'll go back to that. Hey, that's pretty powerful, because what can we now say about this function from a translation approach way back from the beginning? It has a vertex at -1 and -4 down here. Okay, so it's going through like this. So for this function, we've now been able to recover that, this and this. Hey, even though the batteries are flat, we're doing all right with a bit of maths, mate. So let's come down and let's summarise that now. What have we done? Okay, when it's in this form, cuts the axis when y is 0, factorise it by reversing FOIL, or factorising it, put the 2 factors equal to 0 by the null factor law, therefore get the 2 intercepts. Hey, that's good. That one and that one. Now, we have just been able to package it up into perfect square or vertex form, so we can say the vertex is at -1, -4. How accurate is this now? There it is down there at -1, -4. Hey, that's pretty impressive. Do you remember from earlier presentations, there's only one thing left. It'd be nice to find where it goes through the y-axis or the y-intercept. That'd be good. Okay, what would you do? Come down and let's finish off this mathematical investigation here now. The y-intercept is when x is 0, because all along the y-axis we have not gone positively in the x direction nor negatively. So this is when x is 0. And there are 2 ways of finding this. Come over here to this form. You could substitute x is equal to 0 in here, and you'd get y equals 0 squared plus 2 times 0, take 3. They would wipe out. Right, 0 squared is 0, and 2 times 0 is 0. So the answer would be -3. So the y-intercept would be 0, -3. Does it check? Oh yeah, we've nailed it perfectly without a calculator. Let's do it over in this form. We could substitute 0 in there as well. Let's check it out. It's 0 plus 1 squared, take 4. Substituting x is 0 in the formula to get y. Remember, any of these equations are rules that the y value must obey in relation to the x for the point to be on the curve or the line. So 1 squared is 1, take 4, it still gives you the same answer. It may be a bit easier to do the first one over here. because you can see those terms are always going to wipe out if you put x as naught in there. And so the y-intercept is always a number down the end in that form. It's a bit more hidden in this form over here. Now we can do everything. That's pretty exciting. Let's have a look at what we can do here with this graph. So there's the vertex, neg1, neg4. It's always symmetrical about that. So what we can do here is draw that line of symmetry, which is always x equals the x value of the vertex. And then equally spaced on either side are the two x-intercepts. Then we have the y-intercept at neg3. And of course, equally spaced over this side should be a symmetrical point. This one here, I think. Okay, the same distance the other side. So that's sort of a freebie point based on symmetry. You haven't actually had to work that out. Okay, just rub that out here and just say, well, across here, it's there, I think, that point there, we would get it, and you can draw a nice graph. Okay, due to this axis of symmetry, because we know the parabola is symmetrical. Okay, let's go down and have a look at what we might do. So here's some exercises. These exercises are actually taken from Hayes and Harris now, and I want you to try and put in this form and state the coordinates of the vertex. You might also like to try to find the y-intercept by putting x is equal to naught. You might have some trouble finding the x-intercept. Experiment with that, and it's be interesting to see what you find, and then you might check it on the calculator for the graph that you've drawn and see how accurate it is compared to a calculator graph. So have a good look and investigation of that. The question is, though, are you going to fall into trouble here with the x-intercept? I think you will. Okay, have a go, pause the presentation. Straight underneath now are some graphs for you to check. Here we go. Here are some graphs now. There's the first batch. Some of them don't intersect the x-axis at all. I want you to check whether you can get the turning point using completion of the square and the y-intercept. Come back to the x-intercept later, and there's the other batch of them. How did you do? You might have to go back and check that a bit. Some of these with fractions and down the bottom here are a bit harder. Okay, might have to look at those. All right, let's go on. Let's continue the journey and really nail this quadratic function. So here we go. What did you find with the x-intercept back there? You found that where it cuts the x-axis, you wanted to put the function equal to naught. So x squared takes 6x plus 3 equals naught. But there was problems with that because that does not factorise. Okay. We can't find numbers multiplied together to give 3 that total 6, neg 6. So this one we couldn't do. Well, hang on, can we do it by using this form? It cuts the x-axis when y equals naught. So let's see what we can do. X take 3 squared take 6 equals naught. There's two ways of doing this. Pearson's, we'll look at in a minute, likes to call this a difference of squares because 6 could be thought of as a root of 6 all squared, that way, and then we could say this is x take 3 plus root 6 by x take 3 take root 6, difference of 2 squares, a squared take b squared, and therefore x take 3 plus root 6 is naught, or x take 3 take root 6 is naught. So x is, put the 3 on the other side, x has had 3 taken away and root 6 added. Let's do the reverse, add root 3 and take root 6, or on this side add root 3 and add root 6, reversing those signs. So now you can see why it didn't factorise, because it's what's called a surd form. A surd is involved here, root 6. A surd is a number with a radical or root sign in it, cannot be simplified from that. So that it doesn't cut the x-axis at nice integral values, and therefore you won't be able to find over here factors of 3. They were these sort of numbers multiplied together, and to give that middle term minus the sum of the roots. Too hard to detect. Okay, what about another way of doing this? What could you do here? You could say, well, x take 3 squared, take 6 was 0. Let's add 6 to both sides. Okay, and then x take 3 was, take the root of both sides, plus or minus root 6. Okay, and then add 3 to both sides. It's 3 plus or minus root 6. Same answer. X was 3 plus root 6, or x is 3 take root 6. What do you like? You can do it either way for this particular type. So you can see now, if they aren't nice whole numbers or fractions where it cuts the x-axis, where they are surds, you'll need to use the perfect square form and put that equal to 0, because you can't easily factorise it. Do you get it? Want to have a go? Let's have a look. Here's some examples from Pearson's now. So here are 2 for each of the following expressions. They don't tell you, but you can't factorise it. So they want you to complete the square and then put it equal to 0, see where it cuts the x-axis. I'd like you to sketch the function as well. Sketch the function, because you'll be able to do everything with this one. Let's have a look. Here's the first one. What have they done? Halve the coefficient of x, 6 over 2, square it and add it on, take it off, and bring the 3 down. Okay, so this is y equals, and we go to there, and therefore package it up. The square you have on the end is always this number here. Okay, so it's x take 3, neg 9 plus 3 is neg 6. So believe it or not, that's the same expression as the one up there. But gee, isn't it good? Because I want to do this along here as we go, because we're on a quadratic journey here. So this would have a vertex at 3 and down at neg 6. Okay, somewhere down here. So we've got the vertex there, neg 3, plus 3 there, and neg 6, using our perfect square form. If y equals that, now we're going to put it equal to 0. So here we go, I'm putting it equal to 0, factorise it, put it equal to 0. One of the factors itself must be 0, null factor law, so we get what we had before. So now, just extend this axis a little bit. We can come out here to 3 plus root 6. Root 6 between 2 and 3, isn't it? So it's out here just past 5, somewhere there, and 3 minus root 6, somewhere in here. Where's the line of symmetry? Draw it there. It's in here somewhere. We'd have to be careful with our scale. So it'd be like that. 3 minus root 6 and 3 plus root 6, just coming in on the positive side there. Okay, and this would be the vertex 3 neg 6. What would be the y-intercept? They haven't asked you to do that here. But let's put x is 0 in this expression. Y, so x is 0. B3 would go through up at 3. Is that right now? Let's just have a look. Yep. So 3. So my drawing isn't too good here. 3 neg 6. It's going to, oh yeah, so it's, see there, it's really over more on the positive side of the x-axis coming through here, and it's up about 3. They really need to draw this on graph paper. So it goes through there at 3 take root 6, which is just slightly positive, and ends up going through at 3. Wow, we can do a lot with this if we keep thinking about the graph of the quadratic function as well as just the maths, just the algebra of it. Let's have a look at this next one. X squared plus 5x take 2. That won't factorise either. Very easily put equal to 0. So let's complete the square. So half of 5 is 5 over 2. This was some of the harder ones from before. Square it and add it on. So that's 20, and then take it off. So here it's 25 over 4. Square the top line and the bottom line. So it's x plus 5 over 2 squared. Take it away. And then what do we got? What's 2? Neg 2. Neg 2 is negate times 2, that'd be neg 16. Let's put this, neg 16 on 4. So neg 25 on 4, take 16 on 4 is, no, hang on, 2 is 8 on 4. Oh, I got it right first time. Neg 8 on 4. So it's neg 33 on 4. Bit messy with fractions now. Okay, so what's our square? X plus 5 over 2 all squared. And here then we can call 33 over 4 root 33 over 4 all squared, if you want to do it that way. Out at this stage though, if we put this as y equals, we have a vertex at neg 5 over 2 and neg 33 over 4. Messy numbers, we can still deal with it. And if you make this a factor and then put it equal to 0, get some messy numbers. But here it is down here, those two values again. Or remember, you could go at this stage here, where are we? Back up here. You could go at this stage to x plus 5 over 2 squared equals 33 over 4. Take the root of both sides. X plus 5 over 2. Don't forget the plus or minus. Two numbers squared give a positive there, so it's a negative times a negative is a positive, so you've got two answers. So you've got x equals, take that away from both sides, neg 5 over 2 plus or minus root 33 over root 4, which is 2. So putting it all together, you could put it, we'll just leave it like that, it's neg 5 over 2 plus root 33 on 2, or neg 5 over 2 take root 33 over 2. Alright, what does that look like with a graph? Well, those fractions are fairly hard to deal with, but if you had squared paper you could do it. It would be neg 5 over 2, so be neg 2.5, somewhere in here for that axis of symmetry. Neg 5 over 2, neg 33 over 4, come up here. That's neg 8 is 32, neg 8 1/4, so it's down here at neg 8 and a bit past that, neg 8 1/4, so we've got coming up like that. Where are the x-intercepts? Neg 5 over 2 plus root 33 over 2. Root of 33 is about 5.5 or something. So here it's neg 2.5 plus, bit hard, neg 2.5 is here, and then we're going to add what? 5 over 2, 2.6. So it's going to go through just there somewhere, fairly close there. And then neg 5 over 2, take root 3 over 2 will be way out here. We're getting a bit of a mess here. You have to calculate these values and put them in. Okay, so this is the point, neg 5 over 2, neg 33 over 4, getting it all together. What's the y-intercept? Let's go back up and check the original function. It was neg 2. So this point is 0 for x, neg 2. So they get fairly hard with these fractions, but you could convert them to decimals and plot them out. Okay, let's look at another one. We're getting pretty good now, so let's keep at it. Not much further to go now. What about x squared plus 6x take 2? That one there. And in this particular case, we will, what? Halve the coefficient of x, square it, add it on, then take it away, bring the neg 2 down. So this then should be a perfect square. X plus 3 squared, take 11 equals 0, and you can call a difference of two squares and factorise it, get those answers, or as we said before, put the 11 on the other side and take the square root of both sides, plus or minus root 11, subtract 3, right, neg 3 plus root 11, or neg 3 take root 11. Okay, and then back up here we could say the vertex of this function was neg 3, neg 11, and draw a graph. What would the y-intercept be? Come right up the top. Y-intercept would be at neg 2. Okay, so let's try to draw it. It's better on graph paper and converting these to decimals, but it's going to have a vertex at neg 3 and way down here at neg 11 somewhere. So that's going to be an axis of symmetry. Vertex at neg 3, neg 11, going through at neg 2. Oh, neg 2 is probably more up there because this is neg 11 down here. Okay, and what's the vertex, what's the x-intercepts? Neg 3 plus root 11. Root 11 is just over 3, so this is going to go through just in here somewhere. And then over here at neg 3, be down at just past neg 6. We could work that out exactly. And we're going to get it all in now. We've got that one, the y-intercept, the other x-intercept. Put some arrows on it. The vertex. And also the axis of symmetry, x equals neg 3, right through the vertexes and axis. How powerful is that? Okay, now there's one less trick. There's a few tricks coming up here. If there's a common factor in the quadratic equation, the easiest way of handling it, like this one over here, if there's a number other than 1 in front of x squared, that's your clue, because we only do monic quadratics here. That's with a coefficient just of 1 there. Then we handle it in a different way. Oh yeah, so there's the 2 out the front. See it here? Got the 2 out the front, and we said, well, what do you multiply 2 by in here? Get 2x squared, it's x squared. What do you multiply 2 by in here to get 4x? It's 2x. What do you multiply 2 by in here to get neg 6? It is neg 3. So it's a reverse of expansions when we're doing this factorising. So let's get rid of that 2 for a start, and therefore if we divide both sides by 2, we'll have x squared plus 2x take 3 equals 0. And then, of course, we can factorise this one. We'll always try factorisation rather than completion of the square. Completion of the square is very time-consuming. So what do you put in the front of the brackets? X and x. 2 numbers multiply together to give neg 3. Could be neg 3 and 1, or 3 and neg 1. What wins? You want a positive 2x at the end, so the larger size number will be positive. So we'll put a positive there. It doesn't matter which bracket you put in, a negative there. Neg 1 by 3 checks, neg 3. But here, if you look at the product here, neg 1 by x is neg 1x plus 3x. So you end up with a positive x. A positive 1 wins here. So when you're picking the factors here, you'll choose the larger size number to be positive, so you end up with positive x term. Okay, let's go down. I want to tell you something. I want to tell you something very important. There it is. You have the power, you've got it, but you've got to practice it and develop it. You've got to use it, otherwise you lose it. You've heard that before. You have the power. Let's come down and see if you can do some problems now. These are from Pearson's now, and I'll take them in the sections. So here is question 1 to 3, and I want you to go through and try to do completion of the square and factorising, equate to 0, and solve the quadratic. And also, though, I want you to sketch the graph as well, please. Sketch the graph and have the y-intercept. Let's get it all together, not just the pieces here. And then go on, do some of these. No need to do all of them, I don't think. Don't forget to take out the perfect square, the common factor there of 2, to solve that one, and so on. So practice your skills now. Let's go on and look at the answers. So there are the answers now to those 3 questions. Okay, so go back and check. Make sure you're able to do them. Some of these square things are a little bit harder, and just remember there are a couple of ways of getting this. You don't necessarily need to put it like that. You can put the square form. What would this be? X plus 1 squared take 6 equals 0. X plus 1 squared equals 6. Okay, adding 6 to both sides, then taking the root of both sides, plus or minus root 6, then subtracting 1. Neg 1 plus or minus root 6. Okay, so there's that way of doing it as well. Alright, so choose what you want. Both are mathematically sound. Okay, let's do some more understanding questions here. Next section in Pearson's, the next level up, solving those quadratic equations. Okay, remember what we're going to do is move all terms usually to the left, but certainly to one side. So you get equals 0, because then you can invoke the null factor law. So don't just use the rule monkey see, monkey do of what the teacher does. Think about the reason. Why does the teacher say move all the terms across to one side? So you will create this 0. Then the null factor law can be implied or invoked, if you like, if you can factorise. So that's the reason why we've learnt factorisation. Okay, so put it all together now. You have the power. Let's use it. So have a go at those two. I'll show you the answers. So pause it. Then come and look at these answers. Okay. Here are the answers. Question 4 and 5. Okay, check them. Have a look. And see what you think. Okay. Let's go down to the reasoning ones here now. Okay, so these are applying the skills that we've learnt to practical problems where squares come about from areas of things and stuff like that. You will get squared functions. You want to look at using your skills on those. So have a go. There's 6, 7, 8, and 9. I'll take you down to the answers now. Okay, so there they are. In practical problems, you often get some funny answers. You would expect that. Practical things aren't necessarily all whole numbers, all perfect fractions. You get some other decimals in there as well when you're using maths to model things. Okay, modelling in mathematics is making up a mathematical description of a practical situation. As such, you might not get all nice numbers all the time. Okay, let's go down and finish off with some open-ended questions here. Okay, write a quadratic equation that gives solution containing surds. Remember, they are square root expressions. Had some of them earlier. What sort of equations are those? Well, those are equations that when you have numbers here, there's a number in here, times x and another number, you can't find numbers that multiply together to add up to that or to come to minus that. Remember the product here, we get a product here and they've got to have a sum or difference in here. That product may not always work. Think about that. You've seen one before that didn't work, and then that's going to give you square roots in your answer, and you can show that by using the perfect square form, plus x plus or minus some number plus another number equals 0, and you can show that that's going to give you that square root or surd type expression. Okay, let's go down and look at the answers. So pause that, have a go. We go down to the answers now. Okay, now your own equations here, you're going to go for check, get the teacher to check those now, because you might not get them right. But you can prove whether you're right by solving the equation using completion of the square. So are you feeling powerful? I think we've almost nailed everything now. We're going to a final presentation, or two more to come. One where we try and put it all together in fairly simple form, and the last one then, what we're going to do is look at technology. We're going to turn that calculator back on, mate, and see what it's got to offer. It's going to be a lot easier doing it that way. All right, look, I congratulate you on coming so far. You're doing well. Remember, you've got the power. You need to practice it. So catch you later. It's cheers for now.